Welcome back to the GCSE Maths Pro YouTube channel. In today's video, we'll be looking at topics that are most forgotten about. So here is a list of some of the topics that you might have likely forgotten about, mostly from Key Stage 3, but that do actually still come up in the exams. So this is a good way to recap some topics so that you don't miss out on any of these marks. So multiplying decimals is probably something you've forgotten about, given that obviously you've probably used your calculator for the last few years, but this often comes up in the non-calculator paper. There are obviously different ways to do this. The way that I like to do it is I like to make both numbers whole numbers. So whether that's multiplying by 10, 100, 1000, whatever it is. In this case, can you see that the first one, I need to move the decimal place twice. So that means multiply by 100. And the second one, I need to move the decimal place just once, which means multiplying by 10. So instead I'm going to do 625 multiplied by 59. Just at least then I don't have to deal with any decimals, and we'll put them back at the end. Now, the way I'm actually going to multiply this is I like to use column multiplication, which might also be another skill that you haven't done recently. So obviously write them in a column, multiply. We start off with 9, and I multiply it by each of the numbers above. So 9 times 5 is 45, so obviously the 5 can go here, and the 4, which is 40, is carried. 9 times 2 would be 18, plus 4 is 22, so 2 here and the other 20 would be carried. 9 times 6 is 54, plus 2 is 56. And obviously the 5 is carried, but that's just there, isn't it? You can write L 5 if you want. That's the first one. Now I need to multiply by 5, but it's not just 5, it's 50, isn't it? So I would first put a 0 here to account for that scale. Then I can do 5 times 5, 25. Again, put the 5, but I'm carrying the 20. 5 times 2 is 10, plus 2 is 12, so carry the 10. 5 times 6 is 30, 31. Carry that 30. Now I can add them. So column addition is just literally straightforward from right to left. So 5, 7, 8, 6, 3. Okay, so these are all the digits, but I obviously need to put it back into the correct scale because think about it, that's basically 6 times 5, 6 times 6, isn't it? Is not 36,000. So there's two ways of doing it. If you've kept track of what you multiplied by originally, do you see how I multiplied by 100? Or I moved the decimal place twice. And on the other one I multiplied by 10, which is moving the decimal place once. In total, that's multiplying by 1,000, isn't it? Or, in other words, moving the decimal place 3 times. So based on that, you just do the opposite and go, right, move it 3 times back. So 1, 2, 3, which is the same as dividing by 1,000. Or the other thing is you just look at the whole numbers originally, 6 times 5 or 6 times 6, however you want to look at it. That would be around 30, 36. So you could put the decimal place here because that creates 36 point something. So our answer is 36.875. So in the same vein, we've now got dividing decimals. We need to know how to do both. So I do the same thing. What I would do is I would obviously make them whole numbers, but with dividing specifically, what I will do is I will multiply by the same number. So with multiplying decimals, we just figured out I need to multiply by 10, 100, 1,000, whatever it is on each number to make them whole. In this case, I would keep it consistent. Now, with this example, it is actually the same. But even if it wasn't, I would say multiply, let's say this one obviously by 100. I would then automatically multiply the second one by 100 or whatever the biggest value is. If the biggest one is 1,000, multiply both by 1,000, for example. In this case, 100 works, luckily, for both. So that's 1,812 divided by 75. Just so you can understand, let's say if I had 18.12 divided by 0.7. Now you can see that the first one needs 100, the second one only needs 10. But with dividing, I would still multiply them both by the same value, the biggest one. I'll show you why at the end. So whatever the biggest scale is that you need to do it to both. Okay, so now we're going to divide. I would obviously just use bus stop. The one you're dividing by goes on the outside, if you can remember how to do that. So obviously 17 doesn't go into 1, doesn't go into 18. So then I'm going to move on to just looking at the first 3 digits, which would be 181. 75 times 2 is 150, so that's 2. And then remainder would be 31, which would go above this second 2 here. How many times does 75 go into 312? Well, it actually goes in 4 times. And then there's still a remainder. So that's when I start putting zeros over here. Now my remainder is 12. So it's actually 120. That goes in once with a remainder of 45. So then how many times does 75 go into 450? Now this is actually a whole number, isn't it? That goes in 6 times. So I can stop there. Once there's no longer a remainder, I can stop there. Now, because I multiplied both by the same scale, I did both by 100. When we're dividing, I therefore don't need to change the scale back at the end. This is just the answer. 24.16. So as long as you do that, as long as you change both numbers when you're dividing by the same scale, you then don't need to worry about the scale at the end. This doesn't work with multiplying though, okay, so ignore that for multiplying, this only applies to dividing. So it says write 27 as a product of its prime factors. So I like to do this as a prime factor tree, so I'll put 27 or whatever the number is at the top, and then we'll split it into 2. Now, there are 2 ways to do this. Either you just write down any 2 factors of 27 that you can think of immediately, and then break those down. I prefer to just go with prime factors. So if it helps to list a few of the smaller prime factors on the side, that's fine. So we've got 2, 3, 5, 7, not 9 obviously, 11, ... you know, there's more than that. I tend to kind of use these. Normally my first port of call is either 2 or 3. I go, can I divide it by 2? If it's an even number, this one's not. Can I divide it by 3? Yes. I personally prefer to put the prime numbers on the left. So 3 is a factor of 27, but it is more specifically a prime factor, isn't it? Because at the same time it is a prime number. So 27 divided by 3 gives me 9 left. Then, because 9 is not a prime number, I'm going to break that one down further. This 3 on the left here, I'm going to leave it because it's already a prime number. I'm not going to break it down any further. Then I go to 9 and go again, okay, of my prime numbers over here, which one's divided into 9? Well, it's actually 3, and then another 3. And then you can go and circle the prime numbers, so they should be all the ones on the left. That's how I like to do it. So when it says write 27 as a product of its prime factors, well, we've broken it down into its prime factors. The word product means times, it means multiply. So you can therefore write it as 27 is equal to 3 times 3 times 3. Now, if they do then mention, leave your answer in index form, so like this, index form, that means powers. If you think about index, it's like indices, isn't it? In this case, 3 times 3 times 3 is 3 cubed, isn't it? That's the same thing. So just double check, does it say leave it in index form? In which case you do need to put it as powers. If it doesn't, then 3 times 3 times 3 is fine. And if we did in our calculator 3 times 3 times 3, you would get 27. So we've broken 27 down into its prime factors, into the prime numbers that divide into it. Same question, different number. So we've got write 60 as a product of its prime factors. So again, I start with 60 here. Now, this is where I would say there's 2 different ways to do it. As I said, I would be looking for prime numbers specifically. So 2, 3, 5, 7, 11, ... And I would go, right, which one's going? As I said before, normally I start with 2. So I would half it just to make it smaller. And then I go, right, can I now half 30? Yeah, just keep halving it until it's an odd number. Okay, 15 I can't half, so then I go through my list. What else goes into 15? Well, actually 3 and then 5. Now both of those are prime numbers, so that's when I know that I can stop. I can circle it like this. Now, there are people who would do it like this. I'll just show you the other option, and you might have seen this in your class, and you might prefer to do it this way. They just look at 60 and go, yeah, what numbers go into 60? What factors are there in general? Not specifically prime, just numbers in general that divide into 60. Now, I think naturally you probably would go with 2 and 30, or maybe 3 and 20, or you could go with 6 and 10. Now, neither 6 or 10 are prime numbers, but that's fine because what you'd have to then do is break both of them down further. So you'd go 6 is 3 and 2, and 10 is 2 and 5. Do you see how we end up with the same numbers? We've got 2 2s, we've got a 3 and a 5. So it's whichever of these 2 trees you prefer. I like the first one because I just like to have all my prime numbers on the left-hand side. I know that I haven't forgotten anything or missed anything out because I was focusing on prime numbers in the first place. It's whichever of these 2. These are both valid options, whichever you prefer. So when I write it out, we like to write it in order of size. It doesn't really matter, I guess, but I'm going to write it 2 times 2 times 3 times 5. In index form, that would be 2 squared times 3 times 5. Okay, obviously keep all the numbers separate to each other, but the ones that you've got multiple of, you can write with a power. So I'm going to go through and do my factor tree for both. So in this case, it's prime factors, so specifically prime numbers. So I know I always tend to start off with 2 if it's an even number, so 2 and 12. Then 12 divides by 2 again to get 6. 6 divides by 2 again to get 3. And those are all my factors that are prime numbers. So I've got 2, 2, 2, and 3. I'm just going to list them there. Then I do the same for 72. So I'm going to stick with the 2s because they're even numbers to half them. 2 and 18, 2 and 9, and then 3 and 3. Okay, so 72 is 2, 2, 2, 3, 3. So I've listed it here. You can see I've got 24 breaks down into the prime factors of 2 times 2 times 2 times 3. 72 is 2 times 2 times 2 times 3 times 3. And then we're going to draw some Venn diagrams. Now, obviously on your page in your exam, it doesn't have to look nice. Like, don't be getting your compass out. Just scribble some nice, rough Venn diagram circles. So obviously I'm just going to label each side, so 24 and 72. Doesn't matter which way around you put them. I just kind of put them in order of the question. Now, with Venn diagrams, you always start with the middle. What's in common? The middle is where they overlap, isn't it? So what do they both have in common? So if we have a look here, they both have a pair of 2s. So for every pair of numbers they have in common, you put it once. So that's 1, 2, and that represents both of these, okay? Then they've got another pair of 2s in common, so I'm going to put that again, once. And then they've got a third pair of 2s. Okay, so in the middle I've got 3 2s. I've not got 6, okay, just 3. So 1 for every pair that they have in common. Then they also actually have 3 in common, don't they? So I'll put 3 here. And then see how 72 has another 3 left over, so that goes on the 72 side. Whatever's left over that doesn't go into a pair goes on either side. So you quickly fill that out. Now this is a bit we need to remember. For the highest common factor, we're going to use the bit of the Venn diagram where it overlaps, the middle bit. So this bit here. So in this case, you can ignore that 3 on the outside. And what you're going to do is multiply anything together that's in the middle. So I've got 2 times 2 times 2 times 3. Now you can either work that out or put that in the calculator. 2 times 2 is 4, times 2 again is 8, 8 times 3 is 24. So the highest common factor is the middle bit of the Venn diagram. So what you can do, the other option is you can break down both numbers into the product of their prime factors. So I normally start with 2, 3 and 2, so that one's 2, 2 and 3. 15 is a bit easier, 5 and 3. Now I've got it on the next page anyway. What you then do is draw some Venn diagrams and label them 12 and 15 in this case. And we're going to do exactly the same thing as we did with the highest common factor. So if you've seen that video, you'll know what to do. Any numbers that they have in common go in the middle. So if you look at this list, you see how they both have a 3. So I'm going to put 1, 3 to represent that pair. Now they actually don't have anything else in common. So for the 12, there's 2 2s left over, and for the 15, there's a 5 left over. Now for highest common factor, we looked at just multiplying any numbers in the middle. For lowest common multiple, it's actually the whole of the Venn diagram now that I've filled it out correctly. So the lowest common multiple is all of that, and you multiply them together. So lowest common multiple in this case is 2 times 2 times 3 times 5. Now you might be thinking, well, isn't it just all these numbers times together originally? It's actually not, because do you see how they had 2 3s, but I only wrote down 1. So whatever's in the middle is a pair. You're only going to write it down once. And then you just work that out. So 2 times 2 is 4, times 3 is 12, times 5 is 60. The Venn diagrams method might seem long, but once you've got into the flow of it, it's actually quite fast. So these questions don't normally mention lowest common multiple, but it'd be good to recognise the different styles and types that are actually the same thing. So quite a common one is when you have some trains or some buses or something like that. In this case, I've gone with trains. So for example, 2 trains both arrive at a train station. Train A arrives every 16 minutes. Train B arrives every 24 minutes. So you're looking for some kind of question where some type of event is happening every so often. In this case, it's trains arriving. It could be buses leaving a bus stop. Sometimes I've seen where they've said every so often different colour lights flash, things like that. It's all the same thing. So now that we know that we've got 2 different trains, they both arrive every so often, one every 16 minutes, the other every 24. The question is, if both trains have just arrived, after how many minutes will both trains next arrive at the station? At the same time, basically, is what we're saying. So do you see how that's basically lowest common multiple? We're saying, right, every 16 means there's 16 times tables. Every 24 means obviously the 24 times tables. If they both just overlapped, they both just arrived, when will be the next time? So it's kind of like the next point in which both of their times tables overlap, i.e. the lowest common multiple. So again, there's two ways to do this. Either you can just list out the 16 times tables, list out 24 times tables until you get one that overlaps. Or we can use the Venn diagrams method, which is a bit more of a guarantee that we won't make any mistakes. So I'm going to use that method today. So I break down 16 into the product of its prime factors. So I can just go with 2, 8, 2 and 4, and then 2 and 2. And for 24, again, I'm going to use 2 to get 12, 2 again to make 6, 2 again to make 3. So those are all my prime factors for both numbers. Then we need to get the Venn diagrams. Filling in my Venn diagrams, I first do the overlap, so whichever pairs of numbers I have. I've got a pair of 2s here, so that will go in once. I've got another pair of 2s, so twice, and a third pair of 2s, so 3 times. Then left over, I've got a 2 on the 16 side and a 3 on the 24 side. To find the lowest common multiple, I need to multiply together everything in the Venn diagrams. So the lowest common multiple in this case would be 2 times 2 times 2 times another 2 times by 3. Which gives me 48. So what we're saying is that in this context, 48 minutes, both trains will arrive at the train station. Now they've said after how many minutes will both trains arrive, so that is just the answer, after 48 minutes. So that is it, exactly the same method as normal lowest common multiple, but just in a different context. Show the inequality x is less than 4 on the number line. Obviously, before we start drawing it on the number line, we also need to be able to interpret the inequality symbols. As I've just read it, x is less than 4. Are you comfortable with realising that if that symbol is facing towards the 4, it means 4 is the bigger number, right? X is smaller. If not, the way that I like to do it, which you probably saw in primary school, but to be honest, it's the easiest way to remember, is imagine that this is a crocodile's mouth, and it's going to be facing the number that is bigger. Okay, so if it's facing towards the 4 is bigger, and the x is smaller, therefore it is less than 4, okay? Now obviously x is anything less than 4, it can't be equal to 4 because we haven't got that equal to symbol, have we? It's just less than 4. So in terms of how do we then draw this on a number line, well, you're going to put a circle on top of basically the number they've given you, which is 4. So I'm going to put a circle at 4. Now, as I said, because it's not equal to 4, we're not going to colour it in. Just leave it empty, okay? And then you've got to figure out, okay, well, it's kind of open-ended, isn't it? Saying x is just anything less than 4. Well, that could go down to negative infinity, couldn't it? So then I'm just going to draw an arrow to the left because that's covering anything that's less than 4, isn't it? Any of these numbers are obviously less than 4. So just draw your arrow to the end of the number line that they've given you, right? So it covers everything because, as we said, it's only a one-sided inequality, right? We don't have two parts. So it's anything less than 4. And as I said, don't colour in the circle if it doesn't have the equals to bit, which this one doesn't, okay? Okay, so as I was saying before, we had kind of like an open-ended or a one-part inequality, didn't we? Now, as you can see here, we've got what I would call two parts. We've got, a starting point, which is -1, and then up until 5. This is not open-ended, is it? Okay, we've got a range, effectively. X is between these two values. So in this case, you're going to have to draw 2 circles. Obviously, still just on those 2 numbers. So -1 gets a circle, and 5 gets a circle. Now, the -1 circle I'm not going to colour in, because it's not equal to that, is it? It's just x is obviously greater than or bigger than the -1. However, you can see that x is less than or equal to 5. So yes, I am going to colour in this one. Now in this case, because we've kind of got this range, right, it's not open-ended, is it? It's just between -1 and 5. I'm not going to use an arrow this time. I'm just going to draw a line between them, okay? So still use your ruler, obviously try and draw it a lot more straight or a lot more level than I have. But it's not an arrow, is it? Because it's not open-ended. Okay, it's between -1 and 5. So that is your answer for this type of inequality. And as you will know, we basically just deal with it in the same way, except when we're moving numbers across, before it was from one side to the other, now we're just doing the whole of the inequality. So what I mean by that is, but what I would have to do to get x on its own in the middle is I need to move the 1 and I need to move the 5, don't I? So the 1 is +1, so to move it I have to subtract 1. You're just going to subtract 1 from all 3 parts of this inequality. So -4 take away 1 is going to be -5. Copy the same symbol. 5x plus 1 take away 1 is obviously just 5x, which is what we want. Copy the symbol again. 21 minus 1 is 20. And finally, I just need to then move the 5, don't I? Which I would have to divide by 5, because that's currently 5x, which is multiply. Divide everything by 5. So minus 5 divided by 5 is minus 1. Same symbol again. 5x divided by 5 is just 1x. Same symbol again. And 20 divided by 5 is 4. So that's your new inequality, okay? And now we're just going to draw it as we did before. We need to now have 2 circles, don't we? One with the minus 1, one with the 4. We need to colour in the minus 1 because that one was x is greater than or equal to minus 1. The 4 it's not equal to, is it? So I'm not going to colour that one in. And then I just need to join them up. Okay, this one's arranged. It's not open-ended, is it? We've got x is somewhere between minus 1 and 4. So just draw a line between them. Okay, the last part of this bit of the topic is they could actually reverse the question. So we've obviously seen it where they've said this is the inequality, draw it on the number line. But they could also just give you the number line with the inequality drawn and ask you to write down the original inequality. So write down the inequality for x shown on the number line. We're just reversing it. We're going to go, okay, right, what I would do with this, obviously we would need an x, wouldn't we? Where the circle is, that number, just write that next to the x, so minus 1. Then the hardest part is to figure out the symbol, isn't it? So first of all, before I deal with the fact that it's coloured in, is x greater than or less than minus 1? Is it bigger than minus 1 or smaller? Well, because it's obviously got an arrow to the right, it's covering all of these numbers that are bigger than minus 1, isn't it? So x is clearly greater than minus 1. So I need to face my symbol towards the x. Then I can check, now that I know which way my symbol is facing, do I need the little equals bit as well or not? Well, yeah, it's coloured in, isn't it? So it could also be equal to minus 1. That's literally it. Your answer is x is greater than or equal to minus 1. So the main formula, if you want to work out the total angles or the total degrees in any polygon, let's break that down first of all. Polygons are just 2D shapes, right? So any 2D shape, including pentagon, hexagon, heptagon, octagon, you know, that kind of thing. Any 2D shape is a polygon. It's just like an umbrella term for those shapes. And for example, you should already know that the total angles, total degrees in a triangle is 180. And in a quadrilateral, which is a 4-sided shape, is 360. Those are the 2 that you should have memorised. Beyond that, we don't necessarily need to memorise it because we can use this formula. Now, this formula does work for triangles and quadrilaterals as well, but those 2 you should already know. So you're going to do 180 multiplied by n minus 2. Now, n is the number of sides. So just for example, a pentagon has 5 sides. If you wanted to know what the total degrees or total angles in a pentagon is, you would do 180 times 5 minus 2, which is effectively 180 times 3, and that should give you 540 degrees. Okay, you don't need to memorise that pentagons add up to 540 degrees. You can just use this formula for any 2D shapes. Now, this second one here, as you can see, is basically the same at the top. We just added a little bit extra. That would be for any polygon. It could be a regular pentagon where all of the sides are the same, so, roughly something like that. Imagine that all of those are the same. Or it could be a pentagon in terms of this. This is a pentagon, isn't it? We've got 1, 2, 3, 4, 5 sides. That's not regular though. Either way, all of them should add up to 540. But in a regular pentagon, obviously all 5 angles individually are the same. So if you want to find out the interior angle, so one interior angle in a regular polygon, so any shape where all of its sides are the same and therefore all of the angles are the same, you would do 180 times n minus 2 to work out what the total is, and then just divide it by the number of sides to find one of those angles. So those are the main 2 formulas. They're basically the same thing, just a little bit extra here. Okay, now we're making it slightly more complicated, but still very similar. We've got here that angle A is twice the size of angle B. Work out the size of angle A. So here we can check what shape we've got. Again, it is irregular, but that's fine. So we've got 1, 2, 3, 4, 5 sides, which means it's a pentagon. So I'm going to do the same thing. I'm going to work out what the total degrees in a pentagon is. I know we've just done it, but let's just say we didn't just see that. So 180 times by 5 minus 2, which is effectively 180 times 3. Which gives us 540 degrees for a pentagon. Now though, this is the bit that's kind of difficult. How do I split this up? Because A and B aren't exactly the same. I like to bring algebra into it. You might want to use a ratio. I always label the smallest angle with X. So B is obviously the smaller one, right? Because A is twice the size of B. So A is 2 times as big. So if that's x, what does a have to be? And I'm deliberately using the same letter here in terms of x. If that's twice the size, that must be 2x. So do you see how I could create an equation here? We've got 77 plus 149 plus 71 plus the other two angles, which is x and 2x. We know that that must equal, or must add up to, 540. And the reason why I've used the same letter, so I've not used x and y, for example, to show the two different angles, is because I only have one equation. If you've only got information to give you one equation, you can only use one letter. If you had enough information for two equations, two different equations, you could use two, like simultaneous equations. But we don't here, so that's why I'm using x and then therefore 2x. So if I simplify this and add up all the like terms, collect the like terms, so we get 297 plus 3x. It's literally just an equation, so I just need to solve this. So 3x is therefore equal to 243, and then divide by 3, x is 81. Now the only thing here is that when you've solved the equation, you can kind of think that that's the final answer. Just double check. That's what x is. So we know that b is 81. However, do you see that the question was work out the size of angle A, which is actually 2x. So therefore, to find angle A, I just need to double 81, which is 162. And there we are. There's my answer. So we can also use a bit of algebra if you find that helpful as well. So work out the exterior angle in a regular octagon. So if we get an octagon here, again, regular, meaning that all of the sides are the same, therefore all of the angles are the same. Now, we can use our formula to work out the interior angle. However, we are looking for the exterior angle now. Now, sometimes you might think that the exterior angle must be the bit on the outside, but actually it's not that. If I were to continue a straight line here, the exterior angle is this part. So not the whole of the outside, but if you imagine that each of these carried on as a straight line here, straight line here, straight line here, it's all of these little bits. So first we need to work out the interior angle, and then we can use that to work out the exterior angle. So we're going to use the same formula, 180 times 8 minus 2 in this case, over 8 to work out one interior angle. So the total degrees in an octagon is 1080, therefore individually each interior angle is 135 degrees. We should know how to work out the angles on a straight line. Angles on a straight line, that whole thing there, add up to 180. So if I know that part of it's 135, all I need to do to find out the rest of it, the exterior part, is 180 minus 135 in this case, which leaves me with 45 degrees. So that is the exterior angle. So here we've got work out how many sides the regular polygon has. So we've got a regular hexagon specifically here. We've got two values for the angle, and then we've got a regular polygon. So the first thing I need to do is work out the angle of a regular hexagon. So 180 times 6 minus 2, because I want to know only one of those angles, and it's regular, I'm going to divide by 6 as well, which should give me 120 degrees. So now I know that this one is 120. Do you see how I've only got one missing around that point? So we can use 360 degrees minus all three of those, 120 plus 55 plus 50. That will give me the interior angle for this mystery polygon. So there I have 135 degrees left for my regular polygon. So I know that I've got one interior angle is 135. Again, it is regular, so that's fine. And I can set up my equation, 180 times n minus 2 over n, because it is just one of those angles, and just literally solve this. So let's just rub this out and give us some more space. Obviously, I'm going to multiply by n. And at the same time, I might as well just expand my brackets. Then I'm going to swap the 360 and the 135. So 180 minus 135 is 45n. And then I just need to divide. N is 8. So work out how many sides the regular polygon has. Well, it has 8. It's actually an octagon. And there's your answer. Okay, so for percentage change, our first question, we've got the formula over here in the corner. If you need to refer back to that, we've got here. In 2020, the population of rabbits on an island was 4,500. In 2022, the population of rabbits on the island was 6,300. Work out the percentage increase in the population. So we need to do the change, or in other words, the difference. So I'm going to subtract the 2, obviously, the biggest minus the smallest to get the difference, over the original. So think about the timeline. What was the first number? Well, 2020 was before 2022, obviously. So the original population was 4,500. And obviously times by 100 to make it a percentage. And on the calculator, we get the answer of 40. So that is 40%. Obviously, it's an increase just because it's gone up, hasn't it? But it would work the same for a decrease. You would just say, oh, it's 40% decrease, for example. So as long as you memorize this formula, you can pretty much work out any percentage increase, decrease, percentage change question. Really straightforward. So percentage profit, as we said, is very similar to percentage change. It's basically the same thing, but with kind of more of a context. So we've got the formula in the corner over here, and it works the same way as percentage change because profit is the sales minus the cost, so that's the difference, or the change. And then the cost is normally the original in terms of a timeline. Normally you've had to buy something first before you can then sell it. So that's the original number. So it's exactly the same as percentage change, just with the context. So here we've got Jason buys a pack of 50 bottles of water for $7.50. He sells the bottles for 21p each, work out his percentage profit. So we do also need to work out a little bit more because he's given us 50 bottles as a total $7.50, but then he's told us individually they sell for 21p. So there's a little bit more work we need to do in this case. So you can either work out how much each individual bottle costs by dividing $7.50 by 50, or you can work out his total sales by doing 21p multiplied by 50. That's normally what I would do, but it doesn't really matter. So total sales, you might call it revenue, it's all the same thing, isn't it? Is 50 multiplied by, now we've got in pence and we've got in pounds. So again, convert it whichever way you want, as long as both of them are the same. I like to use pounds. So that would be 21p in pounds, wouldn't it? You divide by 100. So obviously I'm going to grab my calculator. So he can sell them as a total. If he sells all 50, he will get £10.50. So that's his total sales. His total cost was this $7.50 here, wasn't it? So therefore profit is your total sales or your total revenue, what you've earned, minus how much you spent, your cost. So that would be the profit divided by the original. Now he obviously had to buy the water bottles first before he could then sell them. So the original is always the cost. And then times by 100 to make it a percentage, which gives us 40% profit. So it works in the exact same way as percentage change. As long as you remember one of those formulas and how it applies to both scenarios, then you're covered. Now this is probably a topic that you've either not realised has an actual official name and therefore don't recognise it, or you might just have completely forgotten that it exists in the first place. Product rule, or just the word product, is a fancy way of saying multiply. And then counting is, well, we're just counting how much of something there is. So the most basic way to put it is that we're going to be using multiplication to figure out a certain number of something. Now, I'll show you actually the context a little bit more when we actually go through some questions, and you might then start to recognise it. So, for example, Simon needs to choose an outfit. He has 5 shirts, 3 pairs of trousers, and 2 pairs of shoes to choose from. How many possible outfit combinations does he have? So it's something like that where you might have sometimes 2 or maybe 3 different options of whatever context. In this case, we've got clothes, and they've asked you how many possible combinations are there. Okay, that's kind of the gist of this topic. So instead of trying to figure out and list out all the combinations, like, well, if I do shirt number 1 with, pair of trousers number 1, pair of shoes number 1, and then mix them, that would take way too long and it's not that many marks. So that's where we're going to come in with the product rule, the timesing. In this case, you literally are just going to multiply all 3 numbers together. So he's got 5 shirts to choose from, times by 3 pairs of trousers, and times by 2 pairs of shoes. So that's the multiplying, which should give us 30 combinations. Okay, this is quite a simple example because all I'm doing is just timesing together the 3 numbers. They're not going to expect you to list out all the different possible combinations and then count them yourself. Now the next example is kind of like a part A and a part B. The part A is very similar to what we've just done, and the part B then shows us where these questions could differ a little bit in terms of the numbers that we use. So, Julia has to decide on a lock combination. The code needs to be 3 digits, and each dial can be set from 1 to 9. How many possible combinations does she have to choose from? Okay, well, if you think about it, I like to look at the lock one. Imagine a lock in your head with the 3 different dials. When I choose the number for the first dial, how many options do I have to choose from? Well, from 1 to 9, that's 9 options, isn't it? Then, if I were to choose the second digit from the second dial, Again, how many numbers do I have to choose from? Well, 9 again, isn't it? And finally, for the third dial, for the third digit in my code, how many do I have to choose from? Again, another 9. So this part of the example is where it's very similar to the previous ones. What number I choose for dial number 1 doesn't affect what number I choose in dial number 2 and dial number 3. I still have 9 options all the way through. So 9 times 9 times 9 is 729 options or combinations. However, when I then go to part B, you'll see how that could actually then be more specific and differ. So this is like part B of our question. We've still got the same lock, and they've now said if the lock combination cannot repeat any of the same digits, how many combinations does Julia have to choose from? So for the part A, we just didn't account for the fact that actually we would have obviously combinations with multiple digits. So for example, we could have had 555, we could have had 232, they've repeated digits. In the first part of the question, they weren't very specific about that, so we just assumed that we could choose 9 from the first dial, 9 from the second, and 9 from the third. In this case, they've now made it more specific. If we can't have any repeating numbers, we'll go through the same process again. So imagine the first dial. How many numbers do I have to choose from? Well, because it's the first one, I can choose any of the 9, because I haven't chosen any yet, have I? It's the first dial. So I've still got 9 there. However, when I get to the second dial, I've technically already chosen one digit from the first dial, so I cannot repeat whatever that digit is. Now, it doesn't matter which of the digits I chose in the first dial, it's just the fact that I already chose one. So how many options do I have to choose from, or how many numbers can I choose from in the second dial? Now it's gone down to 8. Because whatever that first number was, I can't repeat it, so I can't choose it again. And then if we think about going to the third dial, well, I've already chosen the numbers for the first and the second dials. So I've already chosen 2 numbers. So how many numbers do I have to choose from in the third dial that aren't then going to repeat themselves? Well, that would be left with only 7, wouldn't it? So do you see how in this instance it is slightly different because we're choosing numbers from, if you imagine, the same pool of numbers. We're not imagining the 3 dials as separate categories anymore. We're imagining them as one category. I've already chosen one number, so I can't repeat it. I cannot choose it again. So there's 8 left. And then I choose another number, so then there's only 7 left. And that would actually give us 504 possible combinations. So you can see we've lost just over 200 combinations of the ones that would have repeated numbers. The type of question I'm talking about when I say worded inverse proportion, it's actually ones where they don't really mention a proportion relationship. You kind of just have to figure it out for yourselves. It kind of sneaks up on you a little bit, and a lot of people find it really hard to figure out the actual answer. But I really want to get you to understand that when you read these types of questions, just think immediately inverse proportion, okay? So let's actually look at the questions first. For example, we've got here, it takes 3 builders 4 days to build a roof. How long would it take for 6 builders to build the roof? Okay, now our immediate thought here is you go, well, if it's 3 builders and then 6 builders, that's double the amount of builders, so then it's just 8 days, right? I feel like a lot of us fall into that trap. We go, right, so I've times the builders by 2, so I'll just times the days by 2. But think about it logically. If I have more people, if I have more builders working on the same amount of work, the same roof, ideally, hopefully, it should be shorter, shouldn't it? It should take less time. That's why it's inverse proportion. Because in this example, the more builders I have, the fewer days it should take. So both of those variables, the builders and then the days, are going in opposite directions, aren't they? If I have fewer builders, it's going to take more days. So the way that I would work out, let's say if they're more complicated, is, okay, well if I've got 3 builders, it takes 4 days, I would like to work out, first of all, how long does it take one builder? And again, naturally you're going to go, yeah, I just need to divide like 4 by 3. But no, it's inverse proportion. We need to do the opposite. If I've only got one builder, it's actually going to take 3 times longer, isn't it? So in order to find, in this particular example, obviously one builder, you have to do 3 times 4. So it's actually, it would take 12 days for if I had only one builder. Now, how long does it take for 6 builders? This is when I can actually then divide it, right? Because it's going to be more builders, so therefore a short amount of time. So 6 builders would be the 12 days divided by 6, which is 2. So we get 2 days. Okay, so find out how long it takes for one builder in this particular example by timesing and then divide to find the actual number that they want. Now, often this question is asked with a part B, which says something along the lines of what assumption did you make when you made your estimate? It's pretty much always the same answer, obviously just relate it to the context. We assumed that each builder works at the same rate. Okay, so it's something about the same rate. So just apply it to the context. In this case, the builders worked at the same rate. Because obviously, technically in real life, you can have one builder that's a lot more productive or a lot faster than another builder. So just basically write down, whenever it says what assumption did you make, relate it to the context, but say something along the lines of we assumed that everything was at the same rate. It takes 5 taps, 30 hours to fill a swimming pool with water. How long would it take for 2 taps to fill the pool? If you've got fewer taps but the same swimming pool, it's going to take longer, isn't it? It's going to go the opposite direction. So I want to do first to find out how long would it take if I had only 1 tap to fill the pool, and that's when we do our multiplied. Remember we said in the previous one, 5 taps would take 30 hours, so 5 times 30 gives me 150 hours. So if I only had 1 tap, it would take 150 hours. I actually have 2 taps though, so then I can do the 150 divided by 2, which gives me 75 hours. Again, what assumption did we make? In this particular context, we assumed that the taps, you could say something like the taps fill up the swimming pool at the same rate, or the water comes out of the taps at the same rate. Do you see what I mean? So it's something about the same rate, but to do with the taps or the water. So that is everything on the topics that you've most likely forgotten about. If you found this recap helpful, then you can also check down below in the description to find the full videos if you want to go through any more questions on each of these topics. Otherwise, make sure to like and subscribe and leave down below any questions or comments that you might have.